Welcome to this video on reaction rates. This is an introduction video. It would be suitable for AS level Year 12 content, as well as a kind of extension and summary of the work that you would do in GCSE. So a reaction rate is very simply a measure of how much product is produced against time, or how much reactants are used up against time. Typically on a graph, where here we've got volume of gas, so we're doing a gas collection type experiment here with something like a gas syringe. You'd be looking at getting a curve like this, where we have a fast initial rate of reaction, and this is due to the concentration of the reactants being very high. As they're used up and they form products, that lowers the effective concentration of the reactants. A rate of reaction depends on one of four things. The first one, as we've just mentioned, is the concentration. The higher the concentration of your reactants, the more frequent collisions you'll have. That's what the exam board wants to see, more frequent successful collisions with higher concentration. Likewise, if we increase the temperature, particles are going to start to move faster. As they move faster, they're more likely to collide, therefore having a successful rate of reaction, leading to a faster rate. The third thing to look at is a catalyst. Now, if we imagine a simple energy level diagram, where we've got our reactants R here and our product P here. This would be the activation energy, EA. Now, if I add a catalyst to this, I provide an alternative pathway of lower activation energy. See there how for this pathway, that's a lower activation energy from that reactant level. If I add a catalyst, more particles can overcome the activation energy. If more particles have that activation energy, then more particles can react. The fourth and final thing is surface area. A way to quickly envisage this would be if you have a cube like this, with 4 units, just one square, 4 squares on either side, that gives you 24 in total, 24 surfaces. If I break this into 8 cubes, then my surface area becomes 48. A higher surface area means more collisions between reacting particles, and as we can see, as I crush something up and make it smaller, I expose that inside surface area to allow it to react, so I get a faster rate of reaction if I crush something up. Another thing to talk about is how a reactions or reactants orientation can influence there being a reaction. So if you imagine 2 Lego bricks here, if these two collide, they're in the correct orientation to join together and make 2 blocks. However, if I collide these two in their current orientation, they are in the wrong orientation to have a successful reaction. And it's exactly the same with molecules. They need to be facing the right way round for a successful reaction. The final skill you need to show is to be able to calculate a rate. Now, this is my typical curve. We've gained this experimentally. Obviously, we're monitoring a gas product being formed against time, so that is a rate. But to take this rate at any given time, I'll need to take a tangent from the graph. So if I was to take it at t0, I'd draw a straight line, and obviously you're going to be using a ruler. Like this. I then take the change in y on that tangent and the change in x. Gradient is equal to rate, so my rate is equal to my change in y divided by my change in x. If I do this at different points, what I can see is my tangents progressively become more shallow until the reaction is finished. This shows that I've reduced the concentration of my reacting particles. Obviously, when the reaction's finished, there are no more reactants. One is being used up. It might have been there was a limiting reactant, and the reaction is finished. And we can see this change in rate with these changing gradients of the tangent. So if you're asked to take a rate, take a tangent off your initial curve, plug in the numbers for change in y, change in x, press equals on your calculator, you'll get the rate in that for that graph. Obviously my units, I can always take them. It might be that I have grams on the y-axis, okay? But I take the units of my x-axis, in this case centimeters cubed, and I divide it by my x-axis. That's seconds to the minus 1, because obviously divided. So my unit of rate is cm cubed per second. That's the end of the introduction. I hope this is helpful. Tune into the next video and we'll look at rates in some more depth. Thank you.